Hello, welcome to my talk on physical modeling, Froude Similitude for physical modeling of marine structures. This is the last part of 3 talks on this topic, and in this talk, I will introduce what are the criteria for physical model test, and the examples illustrate how this criteria can be met. This is a video for a model test of 2 wave scan models, which are in different scale ratio, 1/8 and 1/16 respectively. This wave tank test was conducted in the large ocean tank at the Eco-Central Dome in France. This wave tank is 50 meters long, 30 meters wide, and 5 meters deep. These 2 buoys are very small models tested in such a large wave tank, but the purpose of the test is to examine the wave buoy's performance in large waves, especially in the extreme waves. So we may ask one question: what is the smallest scale model suitable for a tank test on principle? Here we are not talking about the practical operations in the test model. For example, in this test, the smaller wave scan model has the diameter of 0.17 meter and a weight of about 0.7 kilogram. On the larger model, we mounted 3 fluorescent balls, but on the smaller model, we have only 2. Suppose we have the geometrically similar systems S1 and S2. Here, S2 is the target small-scale model for tank testing. The dynamic similarity would require the Froude similitude, for which the Froude numbers for S1 and S2 must be same as this. And we can cancel out the constant, the gravitational acceleration g, so we have the relation in this form. So if we take the system 1 as the 4-scale model, and the system 2 as the scale model, and then we can define the scale factor epsilon as this, and based on Froude similitude, we can obtain the ratio of the velocities for the 4-scale device and the model scale device given in this form, which is the square root of the model scale factor epsilon. For example, if we have a scale model of a scale factor epsilon equals to 50. So we can see the 4-scale system S1 in this, and the scaled model would be like this, very, very small. So we can enlarge this. We can see the details of the system S2 or the scaled model S2. So we can calculate the velocity requirement for the scaled model based on the formula as this. So this means, based on the Froude similitude, the velocity of the scale model is about 1/7 of that of the prototype. This is very in favor of the scale model test in the test tanks because we have smaller velocity. And based on this, we can calculate the Reynolds number for the scale model, REM, defined as this, and use the scale ratio for the velocity and the length. We got the expression as this. So we can see the Reynolds number for the model is 1/350th of the full scale model. This means, based on the Froude similitude, the Reynolds number for the scaled model would be much smaller than that of the prototype. Now we return back to the USS aircraft carrier. The overall length of the carrier is 333 meters, and the displacement 100,000 long tons, and the maximum speed over 56 kilometers per hour. That is 30 knots, or 15.56 meters per second. So if we suppose a scale factor of 50 used for testing the carrier model in the towing tank, and based on the Froude similitude, we can calculate the model length given by Lm, so it is 6.66 meters. This is a suitable size for many tank testing. And the model mass is calculated by this mm, so it is slightly more than 800 kilograms. Again, this is the mass of the model suitable for many tank testing. And the model maximum speed, um, is calculated in this formula. It is 2.2 meters per second. And this is very good for the tank testing. So for such a model, the size, mass, and the maximum speed all very suitable for tank testing. And in fact, it can be tested in many towing tanks in the world. For a comparison, the Reynolds number for the full scale model is calculated as about 5 billion, and the scale model is about 15 million. Again, the Reynolds number of the scale model is much smaller than that of the full scale ship. Now we look at the Reynolds similitude. Based on the dynamic similarity, the Reynolds similitude for these two geometrically similar systems, S1 and S2, requires the Froude number for both systems, S1 and S2, are equal, expressed as this. Since we normally use same fluids for the full scale and the scaled model, for example, the sea water and the fresh water in the tank, then we can assume the density are same and the fluid viscosity are same. Thus, we have the relation based on the Reynolds similitude as this. And we can calculate the model speed from the Reynolds similitude. We have the expression as this. Therefore, the Reynolds similitude would lead a larger model speed than that of the full-scale model. Hence, this condition is not easy to be satisfied for a smaller model. Same as the previous example, take the scale factor epsilon as 50. Based on the Reynolds similitude, the velocity for the scale model is 50 times of that of the four-scale ship. And this relation could produce a practical problem on how we can achieve such a velocity for the model. And for a comparison, we can calculate the Froude number for the scaled model given as this based on the Reynolds similitude. And from this calculation, we can see that the Froude number for the scale model would be 350 times larger than that of the four-scale ship. This means, based on the Reynolds similitude, the Froude number for the scaled model would be larger than that of the prototype. So again, we look at the USS carrier, and based on the Reynolds similitude, we take the scale factor as 50. So based on the Reynolds similitude, we can calculate the model length as this. So this is the same length as that for the Froude similitude, because this is a geometric scaled model. And the model mass given as this weight is still good for the tank test. And the model maximum speed is calculated as this, so we can see the model speed requirement would be 777 meters per second. This is a huge speed for a model. So it can be seen the maximum speed required for the scaled model based on the Reynolds similitude would be 777 meters per second, which is so high, no testing facility can satisfy this condition. And based on the Reynolds similitude, we can calculate the Froude number for the four-scale model. We got 0.272, but the scale model, we got the Froude number 96.25. So we can see the Froude number for the four scale and the scale model are very different. From the previous two examples, we can see it is a reality for a scale model. We cannot achieve the Reynolds similitude and the Froude similitude at the same time. However, the similitude laws require both similitudes. In this slide, an interesting example would show how we can achieve the Reynolds and the Froude similitudes at the same time. This is the proposed Sorting's sonar tank, for which the water is supposed to be heated up to 90 degrees Celsius for the model test. For the four-scale ship, the water is supposed at 20 degrees Celsius, while the scale model at 90 degrees. So we can see the density would reduce by about 3% from 999 to 966 kilogram per meter cubic. But the viscosity would reduce from mu1 to mu2. Mu2 is less than 1/3 of mu1. To maintain the Reynolds number, we have this relation, and we can work out this relation using the different densities and viscosities. To maintain Froude similitude, we have the relation as this and this. So if we put this together, we can obtain the scale ratio epsilon as 2.11. This means at 90 degrees Celsius, if the model scale factor is taken as 2.11, which is roughly a half model, the Reynolds and the Froude similitude can be both satisfied. But in reality, there's no such Sooner tank, because it would be expensive to heat the tank up to 90 degrees Celsius. And in many cases, the scale factor 2.11 is too small for practical model test. In this slide, we will examine the practical similitude on how we can achieve this in practical applications. Look at the non-dimensional Navier-Stokes equation. We can see we have two non-dimensional parameters in the equation. That is, Froude number and the Reynolds number defined in this formula. However, for most turbulent flows, Reynolds number RE would be large due to the small viscosity for both water and air. So based on the recommendation in the reference here, we can assume when Reynolds number is larger than 100,000, the fluid viscosity effect, the term with the Reynolds number, would be very small when compared to other terms. Therefore, the viscous terms can be neglected. In the case of a high Reynolds number, the non-dimensional Navier-Stokes equation can be simplified as this. So this non-dimensional Navier-Stokes equation for the transformed standard system can be governed by the Froude number only. This means in the scale model, the dynamic similarities can be guaranteed by the Froude similitude alone. As we have shown in the previous examples, the requirements of the Froude similitude can be easily satisfied for the scale models. This is why for most of the model tests of marine structure, Froude similitude is the sole similitude, and the Froude similitude alone could guarantee the dynamic similarities for the scale model test. Now in this slide, we are looking at what could be the minimum model size. Take the USS aircraft carrier as an example. From the recommendation for the model Reynolds number, REM equals to 100,000. And we also have the full scale Reynolds number as 5.2 times 10 power of 9. So achieve the required Reynolds number for the scale model. The scale factor can be calculated as this, so we can obtain the scale factor would be about 1,400. So based on the scale factor, we can calculate the modal length Lm given by this 0.239 meters, and the modal mass calculated by this would be 0.0376 kilograms. And based on the Froude similitude, the model's maximum speed would be given by this. It is 0.417 meters per second. So this actual model would be very small. It is smaller and lighter than a 10-inch tablet. This example is to illustrate the critical Reynolds number for the scale model can be easily met. Based on the Froude similitude, we can easily work out the scaling factors for different physical parameters. See in the table. Some of these parameters would be used to scale the parameters to set up the test environment. Take the example epsilon equals 250 for a cylindrical oscillating water column wave energy converter. In the test, we need to scale the wave parameters. The wave height needs to be scaled down by 50 here. So, if the wave height in the sea is 3 meters, in the tank it would be 60 millimeters. The wave period is scaled down by the square root of the scale factor. Thus, the ocean wave period of 12 seconds would be about 1.7 seconds in the tank. The other use of these scaling factors is the scaling the parameters from the model test up to the force scale. For instance, the force obtained from the scale model should be enlarged by 125,000 times for the force scale structure, which is given by the scale factor power of 3. This is the cylindrical oscillating water column model test in regular wave with the scale factor epsilon equaling 250. The regular wave height is 60 millimeters and the wave period is 1.7 seconds, but the period of the motion is doubled of the wave period. An interesting motion of coupled motion of heave and roll motion.